right, so hi everyone. My name is Hyunji. I am a rising senior at MIT studying computer science and engineering. And today I'm going to be giving you guys a quick introduction to machine learning, its application, and some words of caution. So for today, I wanted to give you guys a quote unquote introduction. So I won't be going into the theory behind the different algorithms too much, but I'll instead be focusing more on the high-level concepts and applications. Of course, if you have any sort of specific questions about examples or algorithms afterwards, I would definitely be happy to answer them for you. Great. So, okay. And before I start, I'll be asking some questions throughout the talk. So if you know the answer, think you know the answer, or honestly just like have any ideas whatsoever, please unmute yourself and just shout out your answer. If you're feeling a little shy, you can also type something into the chat, whether it be the sort of general or private messaging. And on a similar note, if you have any questions for me throughout the talk, feel free to ask it in the chat. I'll try to monitor it pretty frequently. And alternatively, if I don't answer your question for a while, honestly, just unmute yourself and ask, because I won't mind at all. All right, so with that, let's actually dive into some machine learning. So I guess, the first question that we want to start off with is the most basic one. What is machine learning? So does anyone want to take a stab at answering the question? Either chat or unmute, either is good with me.
Can I?
Yeah, go ahead.
Thank you. It's just my own opinion. So, like for humans like us, we also learn from like past experience. So for the machine, like they learn from like past data. Is it like that?
Yeah, no, that's a great idea. So sort of learning like humans, learning with data. Anyone else with any other ideas?
Yes.
Go ahead.
Yes, I think it's about computing and
Computing.
like artificial intelligence.
Yeah, all right.
Stuff.
Exactly. So I think we're going at some great topics. So we've got an artificial intelligence, thinking like humans, sort of working with data. These are all amazing points. And I wanted to start off with this because I think we hear about it pretty often, and we hear a lot of related terms like artificial intelligence or deep learning. And, they get used pretty interchangeably. And I think that can get a little confusing. I feel like for me, when I first started, I sort of didn't know the difference between AI, machine learning, and so forth. So I wanted to start off with that. So we just mentioned artificial intelligence, and that's sort of the biggest umbrella under which we'll be working under. So artificial intelligence is the idea of making intelligent machines, especially sort of intelligent computer programs. What Alan Turing would have said was he would have put it as systems that act like humans, just like one of you guys said, right? So essentially, it's allowing the computer to problem solve on its own. And machine learning lies under this very big and broad category. And, we can define it simply as the idea of using, once again, the idea of having huge amounts of data to find some types of pattern, like what shows you want to watch on Netflix. And if we go a little bit further, we then come across deep learning. And deep learning, for the lack of a better phrase, is essentially machine learning on steroids. This is because it doesn't really require as much human intervention. And within this sort of deep learning category, we can go even further and we can come to the concept of neural networks, but we won't go into that today because I feel like it'll be unnecessarily complicating a lot of things. So with that, let's dive into machine learning, its different types and applications. So for machine learning, we can broadly classify it into 4 different types: supervised, unsupervised, semi-supervised, and reinforcements. The names are somewhat intuitive, so let's get right into it. And we'll start off with supervised learning. So I was going to ask if anyone had a guess on what supervised learning is, but I guess I already sort of gave you the answer unknowingly, so I'll just get to it. And supervised learning is when we use labeled data sets to train algorithms that classify data or predict outcomes accurately. Notice that we have the emphasis on labeled. So let's start out with a simple example. Let's say we're a shop and we're trying to just sell some cookies. To do that, we want to figure out which customers to target based on information from previous customers. So specifically, we know some information about previous customers who bought it or who didn't buy that cookie, as well as their age and how much money they have. We'll sort of represent this in a table like so forth. I've put in some very random numbers and random ABCs. And let's say we can sort of visualize this in some formats. And let's visualize this by putting the sort of age on one axis and the amount of money on the other. And sort of the graph that you're seeing is going to be sort of the data points of each customer plotted on this 2D graph. So the plus, the green positive signs are going to note customers who bought cookies, and the red minus the signs are going to denote customers who didn't buy cookies. Now we want to find out whether a new customer marked as a purple dot is going to buy a cookie or not. The computer then sort of, given the information about customers and the outcomes, tries to find a pattern to tell us whether the purple dot will buy a cookie or not. But obviously, there's so many ways to sort of create patterns and define rules. For instance, the relationship between the variables and whether the customer buys a cookie or not could be denoted as a simple line, a straight line. Everyone who falls above the line will buy a cookie, and those below the line won't. This perfectly sort of splits up the data sets and will have 100% accuracy. But on the other hand, it could actually be a curved line. And once again, as you see, for the data that we have, everyone above the orange curved line bought a cookie and those below didn't. So what supervised learning does is essentially it's trying to find these best fits based on the data points given to minimize some error that we specify. Now you might be saying, hey, I could do that too, and I don't think I need a computer to do this for me. And for this example, I agree. For just two variables, considering the amount of money and age, we can plot it visually and see for ourselves what the sort of trends look like and calculate what the error is and determine for ourselves whether the next customer is going to buy a cookie or not. However, things can get complex pretty quickly. What if the store has more information about the customers, like where they live, how frequently they visit the store, the number of family members they have, and more? Now, we can't really visually see how the customers who bought cookies and who didn't would be spread out because there's just too many dimensions to consider. If we did want to, well, we needed 2 dimensions for 2 variables. And so carrying that forward, even with just 4 variables, we need to plot it in 4 dimensions. Now, I don't know about you guys, but I'm not sure if I can visualize just 4 dimensions. So when we get 6 variables or 10 variables or hundreds of variables, it's going to be pretty difficult for us to do things manually. And that's where supervised learning comes into play. The system methodically finds what the best rules or patterns to decide, in our case, whether a customer will or won't buy a cookies will be. And in such ways, they make their lives easier for us. In the real world, supervised learning is used in quite a variety of places. So for example, it's used for sentiment analysis. What I mean by that is there's work to identify sort of the demeaning or hurtful posts or comments that should be taken down on social media platforms such as Facebook, as well as work to identify and get help for users who may be suffering from depressions and so forth. So if we're able to identify people who may be suffering through their posts or their comments, we can actually get them help more quickly. Another area for sentiment analysis is used by companies like Amazon to classify positive and negative reviews for them to sort of follow up on and improve their services. So for example, given a review, "I love this cookie," definitely coming back again for another, the supervised learning algorithm would classify this as being positive. Obviously, the sort of variables that you would use for such analysis isn't as intuitive because we're now working with sentences, but essentially some examples of variables that we extract from the sentences are things such as, number of occurrences of words, sort of where words appear in text, number of capitalized words, and so forth. So essentially it follows the same principle of using data that's labeled from one sentence to a given sentiment. And we're able to output sort of accurate sort of predictions. Obviously, none of these variables are clearly indicative of one sentiment or another, but I think that's the beauty of these sort of learning algorithms, that it's able to take these seemingly random variables and create a model that's able to predict accurately. So another use of supervised learning is in the field of image classification. Namely, is it a cat or a dog? We can provide a model with essentially all the different sorts of cats and dogs labeled as a cat or a dog, which actually exists, by the way. People have manually annotated over 3 million photos, which I can't really grasp, but they have a data set for cats and dogs. And after using supervised learning to train on these images, when we ask the system what the following picture is, it will reply that it's a cat. Well, hopefully so, if we've trained a good model. And the variables that image classification uses is a little bit more abstract, since we are working with pixels and oftentimes sort of selections of them for certain types of patterns and whatnot. But overall, the concept remains the same, that we're identifying features and using them to sort of train our model and predict some outcome. So definitely, so to recap on supervised learning, it takes in some labeled data set to classify or predict some outcome accurately. I see the question, how to avoid outliers like above, where I'm guessing it's referring to the comment of it's a dog, but more to come on outliers a little bit later, so watch out for that. But I guess now let's move on to unsupervised learning. So does anyone have any guesses on what unsupervised learning is?
It doesn't guess.
Mm-hmm. Go ahead.
It doesn't guess.
Oh, it doesn't guess?
It doesn't predict what will happen.
It doesn't predict what will happen.
Without predicting the facts.
Without predicting the facts. Okay, I feel like we're getting at some sort of, we're using what the term unsupervised is, which I love. I love that you guys are taking a stab at it. Close. I guess, in a sense, you're right. We're not trying to predict some specific classification. We're not trying to predict, is this a positive or a negative? So yeah, you're absolutely right in that terms. And sort of going further into sort of what that, what do we do if we're not predicting something? Then essentially what we're doing is, I guess, the opposite of supervised learning in a sense. It's used to sort of discover hidden patterns or data groupings without human intervention. And here, what I mean by human intervention is that, the data sets aren't labeled. So we're still working with data, but we're not trying to classify, but we're just trying to group. So we're trying to find patterns that our sort of human eyes or human sort of brains couldn't really detect easily. So let's go back to our example of the store wanting to know which customers would buy cookies or not. It's going to appear one more time. So bear with me in this sort of silly example. So we actually wouldn't know whether our customers bought cookies or not. I show you the green pluses and the red minuses, but our machine wouldn't know that. Instead, given this information of the distribution of customers and their sort of amounts of money and the age that we see, we would be able, the computer would tell us, hey, there seems to be two general groupings of customers. And of course, you might still ask, that doesn't seem to be helpful at all. What do I do with, just the knowledge that there's some clusters of customers? But we can think about this in a different manner. Since we know that there's two groupings of customers, our cookie shop can now sort of set up different marketing strategies to target each group rather than trying to target everyone at the same time. So let's consider the following graph, a different one, for a more concrete example. Our cookie shop had data on the age of the customers along with how much they spent at the shop, which is plotted as follows. And our unsupervised learning model clustered customers into three groups: purple, yellow, and red. We can then understand that there's three different groups of customers: older customers who spend very little, represented in the purple cluster; middle-aged customers who spend a lot, represented in the orange cluster; and younger customers who spend a medium amount. And this is obviously a very big generalization. Once again, we're not going to be working with just two variables. Real stores probably have like a lot more factors that they would want to include. But still, this is in the very general sense, one application of unsupervised learning, which is clustering to identify groups. Companies especially use this to identify what groups they should target and so forth. A related but somewhat sort of different example can also be seen online, where if you're shopping on Amazon and say you searched for or clicked on plates, you'll see like other plates or sometimes even cups or utensils show up in that sort of related and recommended products. This is because these companies have some type of algorithm that group those items as being similar. You can see this also being applied in a wide range of areas, like on Facebook, where you get recommendations for groups or pages to join. Another example is dimensionality reduction. So oftentimes, when training these machine learning models, we'll have a lot of variables in our data. However, you would think that having a lot of data is good, but too much data will oftentimes sort of make training really slow and difficult to obtain any proper solution to the problems. Essentially, you have too much training data, so you can't really sort of focus in on any of the sort of variables at hand. So through sort of dimensionality reduction, we can simplify the data without losing too much information, since there can be a lot of similar information in your data. So this similar information would then be grouped together in through unsupervised learning, and we can remove the redundant ones so that we can sort of cut down on our data set without losing too much information. More concretely, you can also often see unsupervised learning being applied for finding anomalies, sort of finding and avoiding outliers like above. Essentially, by clustering sort of the different data points, you're able to find outliers, those that don't really fit in with any of the other points. This is actually really used in financial settings for finding fraudulent transactions because they often come up as outliers. So yeah, that's sort of an application of machine learning being used in the financial as well as the privacy settings, which is definitely a huge factor to consider. All right, so having learned about unsupervised learning, let's now quickly move on to semi-supervised learning. Once again, does anyone have a guess on what semi-supervised learning is?
You guess a little bit.
You guess a little bit, and that's absolutely right. I think you can sort of guess by the name as well. This is a mix of supervised and unsupervised learning. Essentially, you have a data set where the program uses a smaller labeled data set to first guide the classification part and so forth, and then move on to a larger unlabeled data set afterwards. Essentially, its aim is to get the best of both worlds. Supervised learning is more accurate since it has labels that you can use to check for accuracy. But it's also so much more cumbersome because we need to gather this vast amounts of labeled data, which is very much a manual process. On the other hand, unsupervised learning doesn't need such manual work, but it's also less accurate since it's very possible that we're going to group very different subjects together and we wouldn't even know. So semi-supervised learning then seeks to sort of bring the benefits of both worlds without too much challenges in finding sort of large amounts of labeled data. So at a high level, it works as follows. So you start with supervised learning to train a model that predicts labels on the small labeled data set that you have. Then you use that model to predict the unlabeled data. This might not be totally accurate, which is why we call it pseudo labels. And afterwards, you have a pseudo labeled data set that you can now train on however you see fit. So essentially, going back to our cookie shop example one last time, say we have the following data points, but instead of knowing all of the customers' outcomes, we only know the outcomes of 4 customers. We don't know whether the remaining customers marked in purple have bought cookies or not. Then we train on this data to predict what the purple customers did as follows. So now we essentially, with the 4 data points, created a trend and predicted 100% with 100% accuracy for now on how, I guess, these customers would sort of buy or not buy. And then with the sort of newly labeled larger data set, we run sort of the learning again, and we're able to come up with sort of a refined model on predicting on how sort of customers are going to buy or not buy cookies. And definitely note that the trend lines are probably most likely going to differ from using the smaller data set to the larger data set. And that's definitely the sort of purpose of semi-supervised learning. But sort of, I guess the thing is, when do they get used? For the most part, they're really helpful when there's vast amounts of data just not labeled. For example, a text document classifier, whether it be to sort of assign different topics to articles like food, sports, and politics, or identify parts of speech for each word in a text. There's so much text that can just be easily scraped from the internet. For example, we can simply just create a simple Python program to extract data from, say, New York Times. However, what's difficult is sort of finding the data that's labeled. Manually reading through documents and classifying them as being of some topic, or going through each word to assign parts of speech is super tedious. In such instances, semi-supervised learning comes to the rescue, and we're able to work from small sets of labeled data first before moving to the much larger sets of data that we can get. In a very sort of similar note, semi-supervised learning is used for image classification as well. I know we looked at an example of image classification with supervised learning, but there's so much more images on the web that we can use in a pretty decent number of labeled image data sets as well. So combining this together, image classification tasks are actually a super good candidate for semi-supervised learning. And yeah, so that was sort of supervised, unsupervised, and semi-supervised learning in a nutshell. And I guess to remember is just, are we working with labeled data, unlabeled data, or somewhat labeled data? But now let's go into reinforcement learning, which is our final type of machine learning. And I think for me at least, that's sort of the coolest. So does anyone have a guess on what reinforcement learning is?
Yes. Like is it like improving and like learning from our negative feedbacks? I mean, like if we give like negative feedback, like they will learn from our feedback and they'll try to improve next time. Is it like that?
Yeah, exactly. I think you're right on point. So definitely hitting the key points of essentially this is sort of the closest we get to actually sort of learning in a sense from feedback. So we're going to be sort of getting the machine to learn by itself, quote unquote on itself, because it's not totally by its own, but essentially it's going to go through trial and error, get feedback for each of the actions that it takes, and iterate to sort of improve on its algorithm and improve on its probabilities to get itself to be better. And you guys actually saw an example of this already from Ray's lecture, where you guys learned about creating algorithms to solve Connect 4. And essentially there, we weren't really given any data sets, but we were only sort of told the different rules for how to play Connect 4 and the sort of, and we came up with different algorithms for our computer to build a system that could essentially play Connect 4. So that's sort of the nutshell, but let's sort of start with a, easier, I guess, a simpler example. So let's think of computers as a child learning how to walk. So the computer first starts by sitting down. All babies, I'm sure, are either like on their belly, on their back, sort of on the floor for the most part. It can then the computer then can continue to be in this state of sitting down, or it can start getting up. This happens randomly at the start. And when by chance it starts getting up, the program receives some reward, plus 10 for us. Then, by some chance again, it might sit back down. And here we're going to give it negative feedback. So we're going to say, hey, we don't want to do that because that's not the behavior that we want. And so iterating through, the program now knows, I think I should prioritize standing up, like sort of the process of standing up. And so it stands up again and iterates that process where it stands up a little bit further and continues to, and so forth. So now, once again, we're adjusting the probabilities so that we're favoring further standing up. And at some point, the process will continue and they will be fully standing up, taking their first step. Now we really reward this. As long as they're moving and standing up, essentially taking some steps, we keep rewarding them. So in such sense, we incentivize the computer to continue walking. And just like that, we didn't ever provide the computer or the system with any data on the ideal behavior that we want, nor did we tell it what it should try to do. The computer essentially didn't know that it was trying to walk, but we were able to teach the computer how to walk. This is the fundamentals of reinforcement learning. So the most sort of widely known applications of this type of learning is with games. And as you saw with Connect 4 from Ray, sort of the more complex versions of it is through different games like Go or chess. And I'm sure you've heard of AlphaGo, which really beat the top sort of masters in Go world champions, which is amazing. And essentially what it did is just sort of program in the rules of the games so that it can reward certain behaviors and negatively take off points for some other behaviors. And it sort of learns on its own. For AlphaGo, I believe, I believe they played with humans as well, but for the most part, what they did was essentially build like sort of thousands of variations of AlphaGo and got them to play against each other. So essentially through machines playing each other, they learned and became better versions of themselves. And obviously, I'm sure, Connect 4 had 4 trillion, I think, sort of possible configurations and whatnot. Go is even worse, where there's apparently more than 10 to the power of 170 possible board configurations to consider. So the fact that, we're able to do it without feeding in any data, because trying to consider even just all possible board configurations as data sets would be immense, is super cool. The fact that reinforcement learning just removes the need for data. I think another super interesting application is in the field of robotics. So similarly to learning how to walk, reinforcement learning has been used to build robots that can navigate everywhere and through obstacles, just like sort of we humans or other animals. In this case, dogs can. So here is somewhat of a short clip. And essentially, you'll see that it really mimics the sort of behaviors of a dog, I think. This is from the group Boston Dynamics. And I believe this is sort of modeling a dog. And you'll see that it sort of goes up, goes down stairs. And when it actually sort of meets an obstacle, another dog in our case, it stops. So the fact that through reinforcement learning, it's able to learn these very specific behaviors is really amazing, because we probably can't tell a robot and manually encode all the different rules for how to walk. I don't think I could even sort of tell it what the general rules are. So that's sort of the fun parts of reinforcement learning. And so as such, there's so many cool applications of machine learning that we either already see in real life or is in the research stages. So having gotten like a basic overview of the different types, I wanted to sort of spend our last couple of minutes, I guess 10-15 minutes, sort of diving into some of the more complex and what I think are the more interesting applications. If I can move forward. Oh, there we go. All right, so first of all, I wanted to tell you more about natural language processing, or NLP. You definitely have probably seen this in use, whether it be through asking questions to Siri, or using a virtual assistant or chatbot, or even when using Google Translate. This is inherently a hard problem. A fundamental aspect about us humans is that we are random. We can't really document every single phrase or conversation someone will have with another person. Thus, even though there's vast amounts of data regarding text or conversations to take from, we need machine learning models that will be able to sort of respond to new sentences it hasn't seen before, not just in a way that makes grammatical sense, but in a way that's reasonable. And what I mean by reasonable, you'll see in this example. So this is actually the first version of a chatbot that I built. So it says, if I typed in hi, the bot says, what are you talking about? Seems reasonable, but you get to the next line, I ask, how are you? Bot replies, I don't know. I ask again, what don't you know? Bot replies, I don't know. Once again, I ask, what are you doing? And the bot replies, I don't know. It sort of makes sense. I mean, like technically you could have those conversations, with a very boring person who doesn't know anything in the world. They might respond with, I don't know to everything, but there's no use to a chatbot that just says, I don't know every time, right? So definitely that's the sort of part about being reasonable, in the sense of we're not just trying to make grammatical sense, which the phrase I don't know does, but being able to sort of carry out an actual conversation. And in carrying out a conversation, another aspect that NLP considers is context. So we humans, for the most part, know what we talked about 5 seconds ago. Based on how you train these models, however, you don't contain this context. So for example, if you train the bot by giving one sentence and its ideal reply, the computer only knows to reply based on what sentence it just received. As far as it's concerned, what came before doesn't really matter at all. Let me show you another example conversation which sort of demonstrates this. It's led to sort of pretty interesting results, pretty hilarious at times. So I say, hi, the bot responds, everybody, it's Woody out of something. I asked, what's your name? And you would expect to get back, it's Woody, because that's what he said right before. But no, we get back, me, Willy Wong. We're sort of getting nowhere with this, but I still go ahead and ask again, how are you doing? Bot replies with a little bit of sass, how do you think I'm doing? I say, maybe good. Sort of, it makes sense right now. It says, I don't know. And I ask, was I right? The bot sort of takes on a dramatic turn now, says, you shouldn't have, you. And, I'm a little concerned at this point. I ask again, what did I do? Bot responds, you ruined my life. Interesting, right? Interesting turn. So I ask again, how? And it responds, I don't know how, fire. And at this point, I'm thinking, hey, like, did I somehow build context into my chatbot unknowingly? But no. So I ask, what are you doing? And the bot just sort of changes its gears and says, I bought a couple of tickets. So what happened to ruining my life, right? So I ask again, what's the tickets for? Bot responds, to tear down the walls of Jericho. I'm like, I don't know how that responds well to tickets part, but interesting. And sort of we go on so forth, and we end with, I ask, what is it, to its comment on, wait till I tell you what it is. And we're closing at a totally random note of, I have a letter, ma'am. So as you see here, very sort of humorous conversations. If you just wanted to sort of kill time and have some fun, my chatbot, my very basic chatbot, would serve its purpose. But at the same time, that's not what we want. And that's why the sort of current versions of NLP that you see with Siri, with Alexa, and so forth, actually have built-in context and have data sets that are geared so that it actually takes into account the conversations that came before. If you're wondering why the text is so dramatic, it's because I actually used movie dialogues. And so, movies are oftentimes very dramatic in nature. So it has that effect. And this was actually one of my projects where I was trying to make it dramatic. So one of my very initial versions, but I think it was a fun sort of example. So I brought it here. But obviously, did
Can I go to the toilet for a while?
Oh, yeah, of course. Go ahead. But yeah, so I guess having talked about NLP, we can't really leave out its sort of partner, computer vision. One of the fields that have been explored quite a lot is that of object identification. As you see in the image, given an image, it's possible to detect where certain objects are, whether it be a traffic light, a person, a car, a tree, and so forth. This is a challenging task, however, because there's so many complexities to consider here. First, we need to be able to detect what the boundaries of an object are. Essentially, the computer needs to sort of narrow down from this humongous sort of image, oh, this tiny sort of square here or rectangle here is a person, and it's also holding, and there's also a hand back there. So there's a task of narrowing it down, but there's also the task of figuring out what the object is. Because in the city, you're most likely to see people, cars, stoplights, and so forth. But there's also the chances of seeing an elephant. That chance is not zero. So given the vast amounts of objects that exist, we need to be able to narrow it down to one specific object and sort of not be too general, so that in the city, you're still able to classify that there is an elephant there. And this becomes especially useful in the ever-growing field of autonomous driving. And cars need to be able to drive on roads safely. So being able to detect people, pedestrians walking by, sort of being able to stay within their lines, looking out for traffic lights and so forth. That's all computer vision. So that's a super sort of big sort of application being explored today. Another application of computer vision can be seen with motion tracking. often used in sports, I'd say. Being able to track athletes' sort of movements accurately, especially, allows us to sort of better analyze their performance and improve on it. So it's able to help with their performance as well as sort of detect changes or potential injuries that they might be having. You also see it being used to help those with disabilities, where by being able to sort of track their eyes or slight hand gestures and so forth, it allows people who can't easily use keyboards or mouse to use their computers more easily. So that was on computer vision and NLP. But I think the one sort of last, most recent application that I'm personally really interested in is GitHub's Copilot. They say that it's your AI pair programmer. Let's first see this clip, which is super short. But essentially what it's doing is we're given a information about what we want the function to be, what we want the function we want to write to be. And Copilot, Google's Copilot, essentially fills in the line of code for you. So it's really essentially like another programming assistant that does your work for you. I still haven't been able to sort of wrap my mind around how they did this one, but it's super cool. It just came out a couple months ago, and a lot of people were testing it out and so forth. So maybe one day we don't even need to learn how to program to create a program. We could just get our AI to do it for us. Definitely it's not perfect right now. From what I know, if you erase everything within the function and ask Copilot to fill it in for you, it will be correct, I believe, in just under 50% of the times. And given around 10 attempts, it will be correct for that other 50%. So right now it's supposed to just be assisting you instead of taking over your role, but I'm sure it's getting smarter all the time. So super interesting there. But although sort of machine learning in general sounds amazing, I think I wanted to sort of end on a cautionary note, because I think it's always really good to be cautious of sort of some things when creating or using these models. So let me sort of just get you guys introduced to sort of some things that I want you to keep in mind. First of all, let's consider the following scenario. Given some information about how many hours of exercise an individual performs and their corresponding risk of heart disease, we want some model that will, given how much exercise someone does, output how likely they are to get heart disease. Okay, so here's the graph, with all the data points that the researchers gathered. And the blue line indicates what the computer will predict based on the data. You'll see that the blue line is the current best fit of the data at hand. It's not perfect, obviously, because the points are spread somewhat scattered, but it's the best sort of trend line that we have. But what does this seem to be telling us? Something pretty interesting. It seems to note that the more you exercise, the higher risk of you getting heart disease becomes. Crazy. Somehow that doesn't align at all with what you would normally think. I mean, after all, we're always told that exercise is healthy for you and that you should go out and get some fresh air, right? So what might be going on here? And you might see it if we see another representation of the sort of same data, but instead of just clumping it into the same sort of red dots, we actually separate it out by age range. The red dots explain age groups of the sort of the oldest elderly population, the green the next, and the blue being the youngest population. So now, if we sort of group by age range and create the trend lines again, we'll see that the trends actually sort of match what we want it to, what we would think that it makes sense. The more you exercise, the lower the risk of heart disease becomes. So as such, failing to consider in some variable, in our case, age, could lead to a super biased data set and can drastically change the outcomes of your model. So consider the damage that you could have caused from such mistake, right? if the researchers publish their findings as on the left, that they would be seriously harming our public health. You know, personally, I would have taken it for the better because I don't really like to exercise, but still, you know. So when dealing with data and models, you always have to be cognizant of what you're feeding in, and just definitely sort of make sure, is the results sensible? Am I including in any bias, unwanted bias, and rather than just sort of blindly trusting the model. And this really comes into play because we still think, for the most part, that machine learning models are a black box. Essentially, we sort of feed in some data and get some outputs, but don't understand what went on within it. So we definitely have to be really cautious about what might be happening here. I think definitely this is also a sign that, you know, if you read about some machine learning findings, be a little skeptical. Who knows if the researchers unknowingly made similar biases or mistakes, right? So yeah, but I guess like sort of switching gears, another sort of word of caution is that there could be potential sort of malicious attempts at exploiting your models or causing harm. So for example, consider the following image classification problem. Given this image, what would you classify it as? Just quick answers, shout it out. I'm sure it's very obvious. Not trying to trick anyone.
Very cute.
Very cute. It's a dog. Yep, right. And how about this one?
There's a cat dog.
Cat dog.
A bit more scary. A bit more
Tiger.
scary. It's like
All right,
it's
all right.
more like
Ghost error.
A tiger, a cat, a dog.
It doesn't look like a dog.
It
Mhm.
It no
looks
longer
very
looks like a dog. It no
All
longer
right.
looks like a wild.
Yeah, so a little bit of a mixed reaction there. It was intentional. I created it to be like that, but you know, it sort of has the outlines of the same dog, but has that sort of tigery or cat aspect to it. But what about this one? I think this is going to be the most interesting one. Any ideas on what this is?
Cartoon. Looks like a cartoon.
Is
looks
the
like a
dog
painting.
taking
It looks like
a
a
photo with
painting.
the worst color you can?
Like a painting, I think painting.
Like a dog that was taken when color
Mhm.
camera was first invented.
Yeah, all right. So I think those are great answers. You know, we seem to be generally going towards the idea that it's a dog, but just a really bad photo of it, you know, low resolution of the same picture. And yeah, that's exactly what I would think as well. But let's see what the model predicts for what they are. So the model correctly predicts, as it should, that the first one is a corgi. The second one, however, as you guys had some confusion about it, the model thinks it's a tiger cat. So essentially what I did was I sort of fused on a tiger cat image onto it so that, you know, it somewhat looks like a corgi, but also doesn't. But the last one is probably going to be the most surprising to everyone. It was certainly surprising to me that I could make this image. So the last one is actually going to classify as a tarantula. Yes, the tarantula, the big black spider. I didn't want to put a picture of it because I hate spiders. But yeah.
I love spiders, so it's gonna be easy for me.
All right.
How
you
does
know,
that look like a
there's
tarantula?
Yeah, right. That's the question. How could it be a tarantula? And that's because I intentionally sort of tweak the images. As you can see, the sort of resolution is a little grainy. That's because I added in signals telling my program, hey, this should actually be a tarantula. And it's so subtle that, you know, to human eyes, we would still think it's just a bad image of a dog, right? And that's sort of the worries that we have, the attacks that we might have coming up, because, you know, we could create a great model that classifies these images, but we might also have malicious people, bad people who want to intentionally change up some aspects so that they can get the results they want instead of the results that actually should be given. So definitely, this is sort of an area that under a lot of research, especially because this is posing potential sort of privacy concerns and whatnot. Because of this issue, actually, though, we now train models with adding in some noise and stuff. So with intentional images created so that, it has low resolution or has a lot of noisy, grainy photos, and intentionally manipulate this data set so that these sort of malicious attacks trying to change a corgi into a tarantula won't work anymore. So yeah, on I guess a related note, final sort of example that I want to end on is something called deepfake. Let's start by watching this video. Actually, I don't know how I can provide sound. Maybe I'm just like, it will work.
Which our enemies can make it look like anyone is saying anything at any point in time, even if they would never say those things. So, for instance, they could have me say things like, I don't know, Killmonger was right, or Ben Carson is in the sunken place, or how about this, simply, President Trump is a total and complete dipshit.
All right, so we're gonna stop it there due to time issues. But what if I told you that this actually wasn't a video of Barack Obama? This is actually—
It wasn't a video. It wasn't a video. He wouldn't say like that.
Exactly, he wouldn't say it like that, and that's because this man right here actually created a fake version of Barack Obama.
I know that man.
Yep.
We have to do what the hacker team. We have to do what the hacker team has done.
Let's keep the conversations down a little bit just so that I can finish. But I love that you guys know the man. I think it's definitely, this is definitely sort of a real issue. And I think we're creating a lot of awareness around it. So we're seeing a lot of fun, pranky videos, creating them as a joke, saying things that people normally wouldn't say. Barack Obama would never say things like that especially on the internet, right? But obviously, if people with malicious,
actually, I have a question.
Oh, okay.
Can we hack Alexa or Siri?
Hacking Alexa or Siri. Actually, I believe there's been a lot of attempts. It depends on how you define hacking. It's certainly happened a couple of times in different manners, some involving machine learning, some not. Some actually involve different ultrasonic, not ultrasonic, but different radio frequency and waves. So just trying to hack into operating Alexa when it shouldn't, making it go nonstop, sort of changing up the programs and whatnot. So there's definitely all sorts of malicious attacks that could happen. And, deepfake is just one example of it, because as you see, using this for fun is great, but what if this was used for creating sort of malicious, harmful content, right? So in such senses, definitely, machine learning is an amazing field, something that I'm truly passionate about, but it's also something to be really cautious about when dealing with. And when approaching media, when approaching sort of articles about it as well, I want you guys to also have that sort of cautious eye and that sort of skepticalness, so that you guys are aware of, whether it be the malicious, the bias, and whatnot. So with that, I hope you guys had a better taste of what machine learning involves, and hope you guys enjoyed the talk. If you guys have any questions, I would love to answer them. I actually don't know if we have time, but I'll leave that up to our MCs.
We have a little bit of time, so if anyone has questions, please speak up or send PMs to staff, the usual.
Yes, not a question.
Okay. Sorry, just to avoid audio colliding, can we please have people who want to ask questions raise their hand, and then on the use the Zoom function to raise their hand, and then staff members can call on them. So number 37, your question?
Yes, not actually a question, but I just want to say that how can I say thank you so much for this super interesting lesson. And yeah, after learning this lesson, like I found that machine learning is like absolutely fascinating. Yeah. And so yeah, thank you so much for this super interesting and
Yeah,
also
I'm
valuable
really excited
lessons.
that you liked it. So I'm glad. And yeah, glad you guys enjoyed it.